Okay. So this tutorial has a large number of questions, but at least some of them are straightforward. So who wants to attempt this? Prove that the join and meet operations are commutative and associative.
Hello, sir.
Yes, Vishnu. Yeah.
I can try.
Yeah. So which one are you trying to prove first?
Sir, commutative is so obvious.
So yeah, like this commutativity just follows by definition.
Yes, sir.
So we will try associativity, but which one do you want to pick first? Join or meet?
Join.
Join. Okay. Okay, tell me.
Sir, let two elements X and Y in a set P.
X and Y?
In a set P. P or S any.
Any lattice. Let's call it L.
Yes, sir. Let's call it. Then, sir, by definition of the joint
correct
operator, X join Y equal to supremum of X and Y.
Okay, but yeah, this is only a name. But what is the definition actually? Supremum is another name for join.
Yes, sir.
Okay, but continue. Sorry.
Yes, sir. Okay, then, sir, next step, we have to interchange the position of X and Y because oximus of extension. This, hello?
So, Vishnu, are you trying to prove commutativity? Because, I mean, interchanging position of X and Y.
Yes, sir. We have to show X plus Y equal to Y plus X.
No, that is commutativity, right? Commutativity, we have said it is obvious by definition, and now we said we will be proving associativity, right?
Okay, sir. I am trying to prove the commutativity.
Okay, yeah, but commutativity is true because again we only define the upper bound as something, you know, U is equal to say X join Y. This is equivalent to two conditions, right? Both X and Y should precede U, and second condition says for any U prime which satisfies condition 1, our bound should be before that, right? So that this is what makes it the least upper bound. But you see that there is no role, the order between X and Y plays here. And that's why I said commutativity will just follow from the definition.
Yes.
So this commutativity will just follow from the definition. But what about associativity?
Yes. Then basically we have to show A plus B plus C equal to A plus B bracket C.
Yeah.
Then we
will have to show A or B or C is equal to A join B join C.
Right. Yes, sir. Then sir, we will take a 3 element in a lattice.
Yeah. Then let A, B, C, B, any 3 elements in the lattice. Yeah.
Yes, sir. Then we will assume the right side of equation have you written.
Okay, so right side is this.
A joint. Okay. Then, sir, by definition, it is equal to A joint the supremum of B and C.
Agreed, but you know, I don't want to write it supremum because that's another name for B join C. But you continue. Yeah.
Then, sir, after that, we will follow all the, I mean to say that supremum of A, supremum of B, joint C.
Yeah, so there you are using associativity of, you know, supremum to prove associativity of join. But then, you know, this is the same operator, right? So you're not proving anything. Again, you know, do not confuse this with the usual supremum that you talk about functions and so on. You know, they can be interpreted in the same way. But, you know, unless we prove associativity of supremum, we are still at the same place, right?
Sir, I have written, can I share the screen?
No. That will be, but I understand where the mistake. I mean, you are going to say this is equal to A supremum of B comma C. This is equal to supremum of A comma B comma C, right? And left hand side will also be the same. But then you are assuming associativity for supremum. But then what I'm trying to say is that by calling something with a new name and assuming associativity for the new name will not give a proof. Right? I mean, this is what you are planning to do, right?
Yes, sir.
Yeah. So, but this is only just renaming it, and you are somehow assuming associativity on the supremum, because in supremum, in your mind generates a meaning. That is why you are trying to do that. But a meaning of a maximum, whereas this join and meet are probably more general operators. Okay, like for example, it could be the LCM. It needn't be the maximum. Okay. Yeah. So there is a gap there.
Sir.
Lala? Yeah.
Yes, sir. So, sir, without using any like supremum, can't we just go with the definition, like the definition, as in where we are taking this B join C? We can say that. So basically, we are suppose B join C is basically suppose S1, and that means. That means we are talking about S1, which is greater than equals to B and greater than equals to C.
Correct. Again, call it precedes succeeds, but it's okay. Because again, if you think about greater than, lower than, then again, I think Vishnu also makes that kind of how do you say? Because it needn't be greater than, less than. It could be any operator that you define or that forms a lattice.
Right, sir.
For example, always think about the divisibility lattice, where this could actually mean S1, B and C divides S1.
Right, sir.
Okay.
So I was using that so that it will be easy to pronounce.
Sure.
For that reason, I'm just using. Yeah.
Sure.
So then it becomes A or A join S1.
No, yeah, but by the way, this means two conditions. BC precedes S1 as well as if for any. So this let me call Y. For any S prime satisfying 1, your S should be
less than equal to. Yeah. So then the equation becomes, the right hand side of the equation becomes A join S1.
Okay. So RHS equal to A join S1.
Yeah. Now again, it's if that is S2. Then we can say then S2 is A comma S1 is less than equals to S2, and then for all S2 or SR prime,
satisfying, let me call this 2.
Yeah.
2, our guy should be smaller.
Right. So from these two, we can say this S2 becomes kind of the global maximum.
So that is also true. So if I combine this 1 plus 2, I'll actually get that A, B as well as C. All of them precedes S2. That's what you're saying, right?
Yes, sir.
And
yes,
next.
Sir. And similarly, for the LHS, we will get for ABC, there will be a global suppose.
So for LHS also, I think if you follow the same pattern, you will be able to show this.
Yes.
But there, let me say you get that to be some S4. Because there you may need some S3 equivalent and then S4 equivalent. So your S3 there will actually be A or B, right? And this will be S3 join C.
Yes. So now there I have two approaches. One, I thought that is not the way. So I thought uniqueness will just give us the result both are same. But before that, what I was thinking, I'll just put it. Because S4 also satisfies these conditions. That means S4 is going. So that means S2 is less than equal to S4.
But hold on. In fact, why this is true? But why do you say S2 is S2 precedes S4?
Because S4 satisfies the condition that is present in the RHS.
Yeah. So you should actually say that this S4 here, right? for S2 to precede S4, this is what will help us.
Yes.
But in order to say that, we should prove that S4 satisfies something which the S prime satisfies, which is nothing but these two guys, right?
Yes. Yes.
Right. But is that true? So the question now, you're actually in a very good track. So the question now boils down to, does A comma S1 precede S4? Right. That's all that. If you prove this, that means S4 satisfies the second line, which means S2 by this line. Okay, my mouse is not visible, right? By
yes,
this.
Sir. So I think when we are writing A comma S1, for that S1 we can write B comma C.
Correct. So in particular, A satisfies S4 is already here. You know, yes. You have this A already here, and now the definition of S1 is something which is B or C, right? If I'm correct. Yeah, right. S1 is B or C. So if B or C is less than S4, by definition of the join operator, B as well as C has to precede S4.
Yes.
Okay. So this means S4 satisfies 2, and hence S2 precedes S4. So this is true. Now it remains to show the other way around, right?
Yes, sir.
Yeah,
but similar.
That is a symmetric case, right? You'll have to. I haven't expanded this, so I won't be able to pinpoint as to what equation we are using. Yeah, this is right. Yeah, but by the way, there is also one. By the way, what was your first approach that you said? You said you had two approaches.
Yes, sir. So here I thought, just because we have these two conditions right now, we can't directly say that they are going to be equal. That's what I initially thought. I mean,
we cannot. You are correct that we cannot say they are equal, because these two conditions does not guarantee uniqueness. These are just this only says that both S2 and S4 are upper bounds for A, B, and C. It does not tell about
not that one. The last two. I mean the S4 less than equals to S2 and then S2
how do you conclude from these two guys that S2 is equal to S4?
Yeah, so that I thought this is not possible. I mean, we don't know what the relation, whether because we are generalizing it, right?
Okay. But then thanks for pointing out. This just follows by the antisymmetry, which is a property that any partial order, not even lattices, right? Any partial order should satisfy antisymmetry, and the definition of antisymmetry is exactly this: if A precedes B and B precedes A, then that can only happen if A is equal to B.
Okay. Then it is.
Okay. Right. But thanks for highlighting that. In fact, I wouldn't have emphasized this unless you asked. This is true for any partial order. This is the antisymmetry property that characterizes. It's one of the three defining properties of a partial order.
Right. So right.
Okay.
So for that, actually, the earlier thought was just because uniqueness properties follows. From B and C, we got a unique point, and then from there we got another unique point S2, and in the other case we got S4. Just because they are unique, that satisfies like both. So the conditions that we got for LHS and RHS basically are equal. Just because in both the cases we got A, B, C is less than equals to S2 or S4, and then for any other that is satisfying those conditions, the above condition will be greater than equals to the S2 and S4. So just because both the conditions are same, so that's why I thought uniqueness just property gives us the result.
Sure. Yeah. But thanks, Lina. Very good. Okay, I'm kind of rushing because I know today there is a big array of questions. There is an alternate proof which also I want you to check. Okay, all of you to check. Okay, you can define some new guy. Okay, let me call it some D to be such that all the three guys A, B as well as C precedes D. This is condition 1, and condition 2 is that for any for every D prime which satisfies 1 also satisfies our guy is smaller than this D prime. Okay, so here instead of defining the join, how do I say, pair by pair, we can directly define the join of all the three guys together. Okay, this is very similar to what Vishnu was thinking. If you are thinking about the maximum, this makes a lot of sense. Even for other examples like LCM and maybe all the different lattices that we can come up with, such a thing applies. No? This D is a common upper bound for all the, in fact, you can extend this to any set, not just three elements. You could extend it to any finite set. A common upper bound which is smaller than or which precedes any other common upper bound, right? So this is a common upper bound which precedes every common upper bound. I needn't say every other because D will precede D. So because it's a reflexive relation. So I mean, so again, this is something which I haven't proved, but I'm stating, and I want you to then finish the proof of question 1 by showing that both LHS and RHS is equal to this guy D. Okay, so show that LHS is equal to D as well as RHS is equal to D. Both of them are nothing but this quantity, which is intuitively very clear to all of us, but try to prove it this way. And this intuition is going to be very useful, especially if you are working with joins or meets of very large sets. You will get, otherwise you will get tired trying to find this out pair by pair. Okay, but this the same steps that Lalath did with slight modification will work for proving this.
Sir, like why should like it exist uniquely?
Why should it exist uniquely?
Yeah, why should it exist at all?
That's a good question, because that in the definition of a lattice, we only assume. That's actually a nice question, but I think that won't hurt us, because let me say I'll define such a D if it exists. Okay, but then once I even show this first guy, LHS equal to D, that proof will for free give me the assurance that D indeed exists. Right, but verify this. I might be wrong. These are things, these subtleties you have to really write down the details and think about. Right. Again, I cannot just use the fact that okay, there is an upper bound and so on. So I think the proof of its existence will have to wait till one finishes the argument that LHS is equal to D. Right, because at least in one direction you will be showing that whatever satisfies the property. Let me first define this LHS to be some S2 as Lalath did. Then whenever we show that S2 satisfies all this condition as well as this condition, at that point, in fact, halfway through the proof of LHS equal to D, you would have automatically established that D exists.
Yes, sir.
Right, yeah, but do verify. Okay, I'm also, I don't want to get stuck there at this time. Okay, give 2 examples of non-distributive lattices. Okay, who has first example? So maybe yeah, maybe it's difficult to imagine. Yeah. So what are the pictures you have?
It's like okay, we'll have a 3-2-1 pyramid kind of thing.
What is 3-2-1 pyramid? Is it this what you're doing?
No, like three vertices with and which are coming and meeting 2 of them.
Okay.
And one, yeah.
And all of these arrows I'm not drawing because they are all upward. Okay. So this is what is known as the Hasse diagram representation of any partial order. Any partial order you can actually picturize like this, where the edges are only put again not between every relation, something which are known as cover relation. What I'm trying to say, I mean, this it might already be familiar to you. If X precedes Y and Y precedes Z, then we will only put an arrow between X, Y, and Z. Okay, the X to Z arrow is omitted because it follows from transitivity. Now there is a question as to how do you infer the direction of the arrows, but that follows by the level at which you are drawing something. Every arrow will be directed from a lower level to a higher level.
So this like there is like one more there are three more vertices. One comes below the left and right vertices on the
let me number them for you, okay, so that you can tell me more easily. 1, 2, 3, 4, 5, 6. Where do you want me to draw the remaining 3?
Below 1 and 3.
Okay.
And there will be one from the new vertex and 2. One below the new vertex and 2.
Yeah, so this is 0. Let's say this is -1.
Then there will be one more vertex which will be above the new vertex and 2 and below the top vertex.
Okay, something like this.
Okay. I don't know if it is a lattice though.
Yeah, so here to verify the lattice property, 1 and 2 does not have a meet. It has a join which is 4, but 1 and 2 does not have a meet. 4, 5 is okay. It has both a meet and a join. 2, 3. Oh, 2, 3 also. 1 and 3 have both meet and join.
1 and 2 both come to -1.
No, but oh yes. Through this, right? Correct. So 1 and 2 have a meet. It has -1. Yeah, that is true. But then what about 2 and 3? Same thing, right? -1. Yeah, and but now 2 and 3 have 2 upper bounds, 5 as well as this guy. What shall I call it? I'll call it X. Okay, 5 and X are both upper bounds. Oh no, 2. This I mistook the arrow. It is from 0 to X, not 3 to X. Okay, so this looks like a lattice. Okay, now where does it violate distributivity? What are the 3 elements that you can tell me which will violate the distributivity?
I think it was 1, 3, and 2.
So yeah, but tell me the relation that will violate distributivity. Should I take 1 join 2 or 3?
1 join 2 will be the 4, right?
Yeah. So what do you want me to take? 1 join 2 meet 3, and I have to show that this is not equal to 1 join 2 and 1 join 3. Let us see. What is 2 and this side? If I do 2 meets 3 will be -1, right?
Okay, I think I meant the other way.
That's what. So what do you want to say? So I'll write down what you want to say.
Means like meet instead of join and join instead of.
Okay. And in this case, you will have to show that this is not equal to. Okay. So what is the join of 2 and 3? That is 5. So this is 1 and 5, which means 0 is the answer, right? 0 is their common lower bound, and that's nothing better than 0 is. There only 0 and -1 are there, and -1 is below 0. And 1 meet 2 is, yeah, you have to go down from 1, this 2 to -1, right? This is -1. 1 and 3 have a 0. So this is -1 and a 0, which is equal to -1. Yeah, and this is not equal. So this is an example of a non-distributive lattice. Very good. Does anybody else have a smaller example? actually this lattice has 6, 7, 8, 9 elements. Okay. Yeah. So the smallest example actually involves, there are 2 5-vertex examples. You can actually look up Wikipedia also. Even something as simple as this is a non-distributive lattice. Okay, this is again the assay diagram. By the way, this can also be, one way to put a very concrete partial order to this is consider this set 1, 2, 3, 5, and the LCM. So this will be my 1, this will be my 2, this will be 3, this will be 5, and the LCM of 2, 3, and 5, which is 30. Take these 5 numbers and use the divisibility relation as the partial order. Okay. And your usual, join is the LCM, meet would be the GCD, right? Here also, I think, yeah, let me try this. I'm also not sure which will work. This versus 2 or 3, 2 or 5. So if the lattice was distributive, both these should have given me the same number, but let's see what is there. So 3 meets 5, which is 1. So 2 or 1, LCM of 2 and 1, 2. 2 or 3, LCM. Okay. Okay. So technically speaking, I should not say this is the, I was wrong when I said the GCD and LCM are the meet and the join operators. You should look at this lattice and define that. Because if I say LCM of 2 and 3, that's not in the lattice. But this lattice still has, this is by the way 30. 30 qualifies to be the least upper bound. It satisfies the definition of a join in this case. So this is 30. Similarly, 2 and 5 is also 30. And this will be, hope I did not make a mistake, right? 3 and 5 is 1. Yeah. Okay. By the way, here I think even if you take the, it does not even distribute the other way, but let me confirm before committing. Let me compare this with 2 and 5. What is 3 or 5 is again 30. 2 and 30 is 2. 2 meet 3 is 1. Sorry, here I'm making some mistake for sure. This is an OR. Yeah. 1 join 1, which is 1. Yeah, here also you see the distributivity is lost. Okay. So interestingly, this does not qualify as a sublattice of all the factors of 30 because it qualifies as a subposet, but it does not qualify as a sublattice because the meet and join operators become different under this context. Okay. So yeah, this is one example, and then the next example, which I will leave as an exercise for you to figure out, is something which looks like a pentagon. This also you can actually write it in terms of numbers. 1 will be this will be 2, 4, and let's say this is 3. So this is 1, 2, 3, 4, and else 12 should be there under divisibility. Okay, here also you can verify that the distributive property fails. So these are the 2 smallest examples according to Wikipedia for non-distributive lattices.
So 2 and 3 should be in the same level.
But that does not really, I mean, in a Hasse diagram, something being in the same level does not, mean something. I should not put 2, only when there is a line between, an edge between 2 guys, we have to worry whether we should align them. Because you can actually ask me 2, 3, and 4 could also be in the same line.
Okay.
What is 3 status? Is it better than 2? Is it worse than 4? By the way, this is not a ranked poset. There is something called a ranked poset where you can assign a unique level to each guy.
Okay.
So here actually you can draw 3 anywhere between 1 and 12.
Okay.
Any other doubt here? And 33. Yeah. So show that the join. So this I think I can skip, right? Is there anybody who got stuck with this question? This is exactly, we did it for the only hint I want to give you is that start with this guy. Now you have an or, think of this as a single quantity, one of them as a single quantity, let's say some A. Now you have A or this, but you are already given distributivity of the or. Use that to expand, you will get 4 terms, but some of those terms will be something like, X or with X meet something. Okay, you will get some terms like X or with X meet Y. Okay, so this you should realize that this is equal to X, which is easy to conclude from the definition, right? Because X join something should be an upper bound for X, and because X is there, X is also a lower bound for that upper bound, and hence the only guy which satisfies that turns out to be X. Okay, so yeah, I think this I'll skip, okay, because we have done something which is similar. Okay, what about question 4? Who wants to, anybody other than Vishnu, Abraham, Lalat, any other than these 3? Okay, I mean, does somebody have a thought? Like, I mean, you tried and failed, or it was a question that you left? Okay, fine. Existing 3, you have an answer, Lalat, Abraham, or Vishnu?
Sir, I thought of it. So I think I got only one answer, which I thought can be the join irreducible, which is basically the function that is taking all the elements to M.
Okay, so you are saying M comma. So actually, by the way, maybe I'll do it that way. Any function, I can actually equivalently represent any function from N to M. This object is same as actually tuples, right? Something like, x1, x2, xn, where each xi is in M, okay? Or this is equivalent to the Cartesian product of this set M n times. So I'll represent my elements as n tuples, where each entry is a number between 1 and n. Okay, so what Lalat's example is M comma M comma M n times, right? But
Yes,
is
sir.
this really join irreducible?
So basically, if you compare, because it's point wise, you're comparing, right? So that means if we take any 2 functions point wise, this function would always be always come at the top. I mean,
but
if
the
you
definition of join irreducibility, let me rephrase that. So join irreducibility, we say that X is join irreducible if X equal to Y join something would always imply either X is equal to Y or X is equal to Z. But again, the intuitive way to read the sentence is that you should not be able to write X as a join of 2 other things. Okay, you should not be able to decompose X as a join of 2, and here other is very important, other elements. Okay, this is very similar to a prime number, but again, the differences are there.
Yes, sir. So here the argument was like, if this particular M and M tuples, if that is the number can be that which can be written as Y join Z, Y join Z, then it has to be a part of that Y or Z. I mean,
no, but
other
what
than
about this, Lalat? Like, I can write this as M minus 1 comma M joined with M comma M minus 1 comma all the way. What is the join of these 2 guys?
yeah, this one only.
Right. So this is X, this is Y, this is Z. So X is equal to Y join Z, and both Y and Z are others. They are different from X.
Then I think nothing is possible.
Okay.
Because the same issue was there. Like So I was thinking like if you're taking any in terms of R, so in R2 I was thinking like if you can take any line and then if we take any function that is below that line, then for them the line would be the what is it, the joint irreducible element.
Like, here going to real numbers, there is a small catch there. I'll come to that in the end. But let me ask, anybody else has a, can you give me one example for a joint irreducible element?
It can be 1, 1, 1.
Yes. So this 1, 1, all ones is a joint irreducible element. Right? Because here, here I'm critically using the fact that we are working in the set M. So you don't have something smaller than 1. Okay. So this is what I was having in mind when I was thinking about Lalat's answer about real numbers and so on. So instead of this M, if I put some open interval there, then I'm lost. If I put something like open interval there, then I do not know what is the smallest element there. But here we do not have any such continuum issues. We only have 1, 2, 3, 4 M as the possibilities. Okay. So yeah, good, Sneha. This is one. Any other example?
We can replace any one of the 1 by any other element, I think.
So something like, some x 1, 1, 1, where x is any number between. So, okay. And this, you can also, it needn't be in the first location, right?
Yeah, it can be in any.
X anywhere. So in total, if you think about it, this gives you M times n joint irreducible elements already. Because for each of the n position, you can choose any of the M numbers. But once you do that, all the remaining positions have to be filled by 1.
It should be M into n minus 1.
Why do you think
Plus
so?
1. Because 1 is already there.
You are correct. You are correct. Because if I do it this way, then this all ones will be counted n times, right?
Yeah.
So I should take out a. I should take out a n minus 1 out.
Plus 1 for the ones.
That's why I only took a n minus 1. I subtracted only
Yeah.
n minus 1. I did not subtract. N. Okay. So these are you all convinced that these are all joint irreducible? Like, even if you have something like 1, 1, 3, 1, 1. Let's for an example, I'm taking n equal to 5. Right. This you cannot write as a join of two other guys. Right. Because if you want to write it as a join of some other guys, all these let's say this is equal to x and I want to write it as some join of y and z, then both y as well as z should have 1, 1, 1, 1. Right? Because if they have anything larger than 1, 1 is the smallest possible. Anything larger than 1, then the join will also have the larger number. So these locations are fixed. Now for this location, at least either y or z should have a 3. Okay. There is a distinction between the two cases. For the other 4 locations, both y and z should have all 1s. For this particular location where x has a non-1, either y or z should have that same number as x. Whichever has that then finally becomes equal to x, and hence, that's okay for a joint irreducible element. Now you can also argue that if more than one location has a number greater than 1, you can always split it into 2. You can realize one maximum using y and the other maximum using z. The remaining thing can be the minimum, it can be just equal to x. Okay, so I hope, this question, I think once you see the answer, it should be clear. If there is any doubt, please ask. Okay, so here question 5, any of the people other than the 4 who have answered, do you want to try? Actually, if you use the remark that we had made after proving the FKG inequality, that the domain being R plus is not a huge restriction. You can in fact talk about any increasing functions, any two increasing functions f and g on a log supermodular probability measure defined on a lattice. This should be a one-line proof. Okay. Just because if fg are decreasing, then minus f minus g are increasing. Only problem is that maybe their domain becomes not necessarily into r plus, right? That's the only issue. But now e of minus f times e of minus g by the fkg inequality is lower bounded by e of minus f. This is positive correlation. E of minus g. So this is nothing but e of fg minus e of f minus e of g, which is e of f, e of g. Okay. Otherwise, if you don't want to use that remark and you want to work with positive or non-negative valued functions alone, then instead of minus f and minus g, you will use some m minus f and m minus g, where m is a number that is larger than the maximum value of f as well as the maximum value of g. Okay, so note that you don't have to worry whether the maximum exists or not, because we are in a finite lattice, right? So your domain is finite, hence the maximum will exist, right? So, but if you use these guys, there will be some more cancellations involved. That's all. Okay, this also, I think the hint was given in the class, right? Was there anybody who did not follow this question? Could not able to answer this? Tried and did not, was unable to answer this question? Okay, so here again, I already gave the hint in the class. You define your mu of a set to be product of all the s's in that set ps times product of 1 minus pt for all the t which is not in s. Okay. Then first step is to show that mu of s is log supermodular. In fact, it will satisfy that relation with an equality, right? If s and t are two sets, mu of s, mu of t will actually turn out to be equal to mu of s intersection t, mu of s union t. The way to prove it is use it term by term. Pick any x. If x is both in s and t, there would be a ps. There would be a px square here as well as a px squared here, because x is in intersection as well as union. If it is only in one, you will get a px into 1 minus px on both sides. If it is neither in s nor in t, you will get a 1 minus px the whole square. So term by term, this is equality. And now both f and g you can take to be the characteristic functions of the two families a and b respectively. Your fg, the product function, will automatically become the characteristic function. Your f will be the characteristic function of the family A. Remember, you have to show P of A, P of B is less than or equal to P of A intersection B. So f would be your characteristic function for A, G will be your characteristic function for B. You define these guys this way, automatically without any definition, your f of G will turn out to be the characteristic function of the intersection of the two families. And then probability of or the expectation of a characteristic function is nothing but the probability of the underlying set. So again, I'll only explain more if somebody has a doubt. Otherwise, it's only being careful here. Okay, so that takes us to the last question. This is where I was rushing mainly because I was not very sure how many of you would have solved this. Did anybody get an answer for this, a proof for this?
So this is in the PDF that
Correct.
was sent.
This is in the PDF that I had uploaded, but did anybody try by themselves? Yeah, but actually, I think I should not discuss. Yeah, thanks, Francis, for telling that. In that extra reading PDF that I had uploaded, this comes in. I don't have it in front of me. Yeah, this is comes under the section some consequences of the AD inequality, page number 120. Okay, so page 120 of the Graham's tutorial that uploaded. But again, the idea is quite clever. Okay, so what you do is you define the set of P to be all those prime devices of A1 to AN. Okay, take all the prime devices of A1 to AN, and now you associate a map. Let's say a map from your set A1 to AN to subsets of P, P, which is done via any AI goes to prime devices of AI. Okay, so use this bijection. Okay, now why do I say this is a bijection? Because if I'm given f of AI, I know what is AI, right? AI is nothing but products of all the primes in f of AI. Why? Because remember, these are square free numbers. So equivalently, you can use this definition. Equivalently, A is a product of distinct primes. So you don't have to worry about whether a prime factor gets repeated or not. Okay. So in this case, what would be your LCM of some AI and AJ? Anybody? Can you write it in terms of f of AI and f of AJ? Right? If f of AI has all the prime devices of AI, f of AJ has all the prime devices of AI. What would be LCM of AI AJ? Okay, so I should more correctly, I should put an arrow here, or I should ask what is f of
their union.
Exactly. It will turn out to be their union, and f of the GCD of AIAJ will turn out to be their intersection, right? For the same reason. This will have all the prime factors which are common to both AI as well as AJ. But this is not what we want. In the question that is given to you, you want this guy. Okay. So can we also write what would be f of AI by GCD of AIAJ? What would this be? Can you write it in terms of
AI minus f of A?
Correct. It is f of AI set minus f of AJ, right? Because when you are dividing by the GCD, what you are taking out are the common prime devices. But in a set difference, when you are taking some set A minus set B, it is the same thing, right? I mean, you are only actually, though you are in principle only deleting this area, this red area, this is equivalent to writing A minus B. Okay, I mean, the black area is what is A minus, or the shaded area is equal to A minus. So this is f of AI minus f of AJ. And now if you put in a lattice structure here, you cannot have a lattice just by using the f of AIs, because the GCD of these may not even exist in the lattice. But you can take the whole, the lattice that you should take should be the whole of 2 power p. Then this is the normal subset lattice. The partial order is the subset relation. So these are all members. These are all members of the lattice. This is a member of the lattice. This is a member of the lattice, and so on. So now you define your family A to be all those sets which such that 1 less than I less than. So there are n sets in your family. F of each corresponds to an image of the guy here, and then we know that these kind of guys are nothing but the different set of A. Okay, I'm using the same terminology we used in one of the corollaries because these are of the form some set in A minus a set in A, right? And then we had proved in class that D of A greater than or equal to A, which means this different set contains at least n elements. Okay, so and if n distinct elements, but one of them could actually be 1, right? Because the different set also contains something like, f of ai minus f of ai, which will be the empty set. So the empty set, and if you do an inverse map and see under this map, if your f of ai is the inverse map, then you get 1. So yeah, this different set can contain numbers n, at least n different numbers starting with a 1, which means the largest should be at least n. Okay, so this last part is quite. I also thought if you wanted to help a student, you should have written instead of saying the maximum is greater than or equal to n, you should have put this into a set notation and show that this set contains at least n elements. But I think the reason is that this is a special case of a general conjecture, as it is still an open conjecture according to the tutorial that I have posted. Okay. Any doubts? Okay, if not, let me stop the recording.